So the last time we met, we looked at the basic theoretical underpinnings of Malmquist Productivity Change Index. We mentioned that there are a lot of reformations and extensions. And these are some of the extensions we mentioned. If you observe carefully, you may have observed that I've added a couple more. So some of the extensions include the global frontier shift, which is one of them that we shall do for this very course, global frontier shift. Okay. And then another one like meta Malmquist. Okay, we will not do that. But then the Pastor, Asmad, and Lavelle, the biennial Malmquist, if time permits us, we shall do that. Everything is ready for that. I've mentioned the global frontier shift. We shall surely do that. Okay. Now, we shall do the meta frontier, but not the meta frontier Malmquist. And the other extensions, the global Malmquist Index. Okay, the meta frontier cost Malmquist. Okay, that's a very unique one. And then the global cost Malmquist and the secular global profit Malmquist, the biennial Malmquist when in the presence of negative data. Okay. And then other extensions that are there. So those are the things those are the very extensions of the Malmquist index. But today what we want to do is we want to take a practical data set and work with that practical data set. Okay, so look at the data set. You have DMUs A, B, and C. You can look at it as banks. Okay, banks A, B, and C, or insurance companies A, B, and C, or countries A, B, and C. Okay, or any other DMUs you might think about. Now, in this context, there are two inputs, X1 and X2, and there is one output which has been normalized to 1. Now, the DMUs A, B, and C are in year 1 and in year 2, as you can see. Note that I could have just simply written it as A, B, and C, A, B, and C, created a column called year, and then have 1, 1, 1 for the first year, 2, 2, 2 for the second year. I could have done that. Now, the first thing to do is to plot this data. Because the inputs have been normalized to 1, the focus will not be dealing with the input. Okay, so dealing with the output. So we want to deal with the input. So we want to plot the input. So you plot the 1 against the 3. That's what you do. Okay. And then, so you plot this 1 against the 3. You plot the 3 against the 2. You plot the 3 against the 3. You plot all of them. But be careful and note that the first 3 are in the first year. All right. So that is what we want to do. The frontier technology in period 1 is made up of A1, B1, A1, B1, C1. They will make up the frontier technology. And then the A2, B2, C2 will make up the frontier technology. So when you look at this, I've plotted the A1 here. If you can remember, the A1 was made up of 1 and 3. So you have 1 on the X1 axis, 3 on the X2 axis. Okay. And then B1 is 3 and 2. So that is where it was located. B1 is 3 inputs and then 2 outputs. Sorry, 3 input of X1 and 2 input of X2. And these are all in the data set. And then finally, you have C. Remember, this is an input orientation. Okay, input orientation. So if we were to form the frontier, okay, the free disposability line will go that way. And then this second part would, A1 would join B1 here. And then you can now create another free disposability line there. So that becomes like a frontier. Now, what about the second year? Well, go check the data. You see that the second year, the first one, A2, is 1 and 3. 1 and 3. So you plot 1 for the x1 here, 3. So that will also be at the same point of A1. Okay. And then for the B2, you will notice that the B2 is 3 and 1. So you have the 3 here and then the 1 there. Okay, so that will give you this one. So you have the 3 on the axis, and then you have the 1 on the x2 axis. And that is a point. And finally, the C2 will be here because that one was 2 and 3. 2 and 3 is located there. So on the basis of that, if we decide to join the frontier is going to eat up the first predisposability line here, stretch, come down to hit the B2 there, and then finally the horizontal predisposability line there. So that's how the frontiers are going to look. I'm just giving you a picturesque analysis before you actually see it. So this is a data set, and this is the frontier for the firm. This is the first year for frontier 1. You can see it. We have the radial lines. All of them are showing. The radial lines are beautifully showing there. And then the second one, just as I indicated, it looks like this. Your ability to draw these frontiers are very, very important. Very, very important. Because in the methodology section of your thesis, you are able to draw, you are supposed to create a hypothetical data set and draw them as well. So now we have all the observations, 3 firms, but they are in 2 time periods, so 6 observations. All right. Now let's add some couple of grid lines. We are going to calculate the efficiency scores, okay, for each one of these firms. And please remember that the efficiency scores we are going to calculate are the Farrell efficiency scores. The Farrell, okay, input-oriented efficiency score. Now, the reciprocal of that is the Shepard distance function. And in this case, it will be the Shepard input distance function. Okay. Now, so how do you now call these the efficiency score? We are using theta for the efficiency score. So theta 1 into bracket A1 means that the input-oriented efficiency score of firm or observation A1 relative to the frontier 1. So you can see that the frontier is, the frontier number is the one with the theta. The frontier number is the one with the theta, and the year is the one with the observation. Okay, that's the year, the one with observation. So it's like reading it backwards. The efficiency of a firm A in year 1 relative to the frontier in year 1. So you can have the efficiency of a firm A in year 2 relative to the frontier in year 1, or A in year 2 relative to the frontier in year 2. So that is how we do the readings. Okay. So in this second example, you have the efficiency of a firm A in year 1. So that same A, but you are measuring its performance relative to frontier 1. And this time, that same A measuring its performance relative to frontier 2. So this is how you call them. Okay. And so the value, when you write this, then you now make it equal to the actual value. You're going to do examples for you to see. Now, these 2 efficiency scores, the first one is known as the own period efficiency score. Own period. Why? Because you have the efficiency of a firm in year 1 also relative to frontier 1. You get a point, 1, 1. So that is own period. But then if you look at the second one, is the efficiency of a firm in year 1 relative to the frontier 2. So the periods are crossing. And this is called cross-period efficiency. Cross-period efficiency. Okay. Now, when you look at A, when you go back to the storyline, and you are measuring the efficiency of firm A in year 1 or A1, you are doing the O or radial efficiency measure. And so It is a distance from the origin to the frontier divided by the distance from the origin to the firm. That is how we always explain it, okay? And in this case, the distance from the origin to the frontier is going to be the same as the distance from the origin to the firm because they are all on the same point. So for A, how do you read it? You read it on the x-axis. So the distance from the origin to the frontier is 1. Okay. And the distance from the origin to the firm is also 1. So the efficiency score for A1 will be 1/1. And of course, if you can see clearly, you can see that is the same thing for A2. Remember, I'm using the x-axis to calculate. I can also use the y-axis, okay, to do the calculation. Okay. So how do you do that? You write is the radial efficiency measure from the origin. Okay. So the efficiency of the firm, the radial efficiency from the origin to the frontier is 3. And to the firm is also 3. And you still get 1. So it doesn't matter whether you use the horizontal axis or the vertical axis to calculate, you will always get the same answer because this is a radial measurement. Okay? All right. So what I'm going to let you do is, if you have a question, by the way, you can raise your hand and then ask a question. What I'm going to let you do, so now in this context, you can see that A1 and A2 will all have a score of 1. Okay, a score of 1 because 1/1 is 1 or 3/3 is 1. I want you to calculate, and by the way, we have to identify whether we are dealing with own period or cross period. Own period or cross period. So what I'm going to do is that I'm going to let you calculate the own period efficiency scores. Okay, first, own period efficiency scores. I'll give you an example for you to appreciate it better. So when I say own period, if you are measuring the efficiency of B1, okay, B1 is a kind of a blue firm. It has to be measured relative to the frontier 1. If you are measuring the efficiency of C1, it has to be measured relative to frontier 1, somewhere here. If you are measuring B2, it has to be measured relative to frontier 2 in its same year. And if you are doing for C2, it has to be measured relative to frontier 2. Now, the thing is that some of the numbers you might not see clearly, but your ability to tell me that something over something will indicate to me that you know what you're doing. So I want you all to calculate the efficiency score of B2, the own period efficiency score for B2. Own period, okay? Do that, raise your hand or type it and let me see. Okay. This one is the easiest one. What is the own period efficiency score for B2? B2. Who is ready to show us that? Okay, so let me see what you, Mark, you are correct. The answer is 1, okay? And I like the way, Michael, come on, you've done yours. You have just indicated 3/3 is 1. Excellent. But it could have also been what over what? Who can type that? It could have also been what over what? Instead of the 3/3, it could have also been what? Exactly, 1/1. Okay. It could have been 1/1, and it's still going to be 1. That is the own period efficiency score for B2. Now, guys, let's go to the own period efficiency score for B1. Own period efficiency score for B1. I like when you rather tell me what over what before you give me the final answer, because I want to see where your answer is coming from. B1. B1 will be what? Stephen, you are right. That is 1/1 or 3/3. No, it's not 1/1. It is 3/3, but it can also be what? It is 3/3, but it can also be what? Check carefully. Exactly, 2/2. It can also be 2/2. So that is how you calculate efficiency scores for B1. Now put your scores down. Put them down. Write them down because you are going to be using them. Now let's go to the tricky ones where they are not on the frontier. Let's go to C1. What would be the efficiency score? The own period efficiency score for C1. Own period. We are calculating own period throughout for all of them before we come and calculate cross period throughout for all of them. What is the own period for C1? Now that one is not that straightforward. So I want to see who will be able to crack it. 1 point, okay, the position it says 1.6 over 2. Okay, so you have an idea, okay, 1.6 over this C1. C1, remember, we're not talking about C2. We're talking about C1. Stephen Morrison, you are closer. Okay, it's around 2 point something. Okay, now of course it cannot be 2.5 because you can see that 2.5 it goes to hit the frontier somewhere there, so it will not be 2.5. Okay, so this is where your eye cannot help you. So if this was an exam, what I would do is that I will give you the exact value here. I'll put the exact values down there just to guide you. I'll do that for all of them, but then I'll do it for this one so that you know the exact value. Okay. Actually, some of you are going to be battling between 2.3 and 2.4, but actually you'll get to know that it's actually exactly, okay. Now, sometimes the best way to know is you're going to know that it's somewhere around 2.333. But at least the fact that you are saying it's 2.3 over 3, okay, or 2.4 over 3, is an indication that you have an idea of what the number is. And for me, that's the most important thing. So you keep that. I'll give you the exact number for that. What about C2? Own period efficiency score for C2. What about the own period efficiency score for C2? For C2. Who can give us a slight guess of what over what? And please always remember, it's not always on the x-axis that you are finding their number. You can always also find it on the y-axis. So let me see. Someone says 1.7 over 2. Okay, you have an idea. Okay, you have an idea. Somebody says 2 over 1.5. Okay. 2 over, no, that's not correct calculation. Okay, Michael, check your calculation. Okay. Mark says 1.6 over 2. That sounds logical. Okay, that's our 1.5. Those of you saying that sounds so later on you will come to realize that it is 1.6667. So that's it. That's what I mean by own period. Let me show you the answers that you got. Okay, so these are the own period. Okay. Those of you mentioned the other one to be 2.3. I told you that it was going to be 2.333. That's it. Okay. And then this last one, okay, as you can see, it was 1.6 over 2. 1.6 over 2. Okay. And I'm sure Mark, you got that exactly. But like I said, you will always get a number there. Okay. But if you are doing your own hypothetical data, you will use the software to do that easily for you. Fantastic. So you all know how to calculate own period efficiency scores. My advice to you is that you always master how to calculate all the own period efficiency scores first. Then when you are done, you calculate also the cross period. Another name for the cross period efficiency scores is mixed period or intertemporal efficiency scores. Note the names because sometimes you see the names differently in the papers. Okay. Cross period or mixed period or intertemporal efficiency scores. Now we are going to do that for all of them. For all of them. Okay. So how do you calculate? You see, in this second graph, I have a kind of a grid line there that will help you to track the numbers. It helps you to track. So cross period. Now let me just do the one of them for you. Okay, I'm going to do C first. C1. I'm going to calculate the cross period efficiency. Now C1 is in year one front. So it has to be measured against frontier one. But because it's a cross period, you will now have to measure it against the green frontier, period two rather, on the same radial line, So it's going to be the distance to the frontier, which in this case, when you look at it on the same radial line, it is like about 2, isn't it? If we check it. Now, you can see that this one is helping you. The grid line helps you to know approximately where it is hiding. And it appears that it's about 2. So the distance to the frontier 2 divided by the distance to the firm 3. And so what that means is that for this C1, okay, how do you write it is also very important. Okay, so the theta, okay, of a firm C1, okay, but relative to frontier C1, okay, relative to frontier 2. Okay. The score is going to be, in this context, it's going to be 2/3, okay, which shows that this firm is inefficient. And you can see relative to the second frontier. Now watch it. It's relative to the second frontier. Okay, so you have 1 relative to 2. So that is how I've calculated the cross period or the mixed period efficiency for C1. I want you to calculate the mixed period efficiency for all the rest. A1, A2, B1, B2, the cross period. C1 has been calculated already as 2/3. So you have to do for C2. Okay, so do all of that. I'm giving you about 2 minutes to do that, and then we can look at the answers. 2 minutes to do that. Let's start with the cross period efficiency for A1. That was exactly 1/1, which was 1. What about A2? A2 was also 1. There's no doubt about that. A2 was 1. Okay. And then what about B1? The cross period efficiency for B1, what was that? B1. Okay. That was a little bit tricky. Okay. B1, somebody says 3/3. That is not correct. Eunice, that's not correct. Okay. It's supposed to be around 2.4 something. Yes. So that's fine. 2.4 something over 3. Okay. 2.4 something over 3. It's within that terrain. Excellent. But actually, you're going to notice that it's a little bit more. Because when you look at it carefully, you don't see it. When you look at it carefully, it hinges somewhere here. Okay. It hinges somewhere there. That is where the line cuts the radial line. Okay. Now, let's go to B2. The cross period efficiency for B2. That was tricky. So let me see who was able to get that. The cross period efficiency for B2. Somebody says 2/1. Okay, that is true. Because I told you that the reason why some of you could not give the answer is because you are always measuring it on the x-axis. But when you take this thing and then you trace it on the x-axis, you will not get it. Get a point? You will not get it there. But you, however, know that whichever way it goes is going to cut this line somewhere. It's going to cut the horizontal line somewhere. Okay. And so the point where it will cut the horizontal line, you will know. But why do you use that? Why don't you use the vertical axis to rather measure? Okay. So first of all, you know that it's going to be B2, the distance to the frontier. And the frontier here, it will hit the frontier at this level. Okay. It will hit the frontier at 2. It will hit the frontier at 2. So the value is going to come from here. That's where the value is going to come from. It's going to come from number 2. And then the distance to the firm, in this case, B2. And B2, you can also read that one. And that will be what? 1. And so it is just 2/1. But because you are always looking at the horizontal axis, okay, and because this thing is too long, you couldn't have found it today. You get it? But she did well. I mean, that was an incredible answer, okay, that you gave there. Eunice, you are smart enough to have detected that, is if you didn't look at the answer anyway. You are smart enough to have found that it's 2/1. Now, you can see that efficiency scores, the last time we said it, efficiency scores, input-oriented efficiency scores, are supposed to be between 0 and 1. But then this one is what? 2, which means that the score is called what? What is the name of the score? Who can tell us? Okay. What is the name of that score? For scores that are greater than 1, they are known as, very good, who typed that? Okay, Mark, that's fine. Now you're called super efficiency scores. Okay, so you are going to see that, and that is because the observation is located outside the frontier it is being measured, outside. That is what leads to the super efficiency score. Okay, so let's go to B1. B1, we calculated it. Okay. It was inside the green frontier. What about C1? What did you get for C1? What did you get for C1? I said C1, not C2, C1. Okay, C1. What was the value for C1? So we said that the C1 is going to be around 2/3, okay? And the C2, okay, as you can see, C2, okay, is going to be around 1.6, okay, divided by 2. Or you can say that it's going to be 1.9 here. Oh, sorry. It's going to be 2.4 here divided by 3. So that's how it's going to be. And then you can now indicate all of the cross-period efficiency scores for this. Beautiful. Okay. So if you're able to do well, you will notice that these are the cross-period efficiency scores. Okay. These are all the cross-period efficiency. And you can see the super efficiency for the B2 that we spoke about. Okay. Now listen, you remember that I told you that there was a debate regarding infeasible results. Okay. The results will be infeasible only for some of the super efficiency scores. So it is possible that one of the super efficiency scores, when you estimate it, it will not get a frontier to hit, especially under the VRS, under the variable returns to scale efficiency. And we said this in the last time. So in this context, okay, because we are not using VRS, or because the observations are not really there much, okay, this is not a super efficiency score. But please know that all super efficiency scores are not necessarily infeasible. But all infeasible solutions or infeasible scores are super efficient. So please note, okay, infeasibility, once you are infeasible, you are a super efficient score already. But the fact that you are super efficient does not mean that you are infeasible. Okay? I'm saying this because I sometimes ask questions related to that. Okay? So this is very important for you to understand and appreciate. See, once you have been able to get all the on-period efficiency scores and all the cross-period efficiency score, I'm telling you, you can calculate anything. You can calculate the Malmquist productivity change index, which we are going to do. And then the one we are going to do next time, you can calculate the global frontier shift. And the one we shall do later, you can calculate the meta frontier. And because the principle, they are all going to be using these scores, both the on period and the cross period, both the on period score. So once you have your on period and cross period scores, you keep those answers. All right. The point that I made, that is a point that you see here, okay, in this fact, that sometimes some of the observations are likely to be outside the frontiers they are compared to. And that is what will lead to a super efficiency scores greater than 1. And this only happens, okay, under the mixed period efficiency estimations. It doesn't happen under the own period efficiency estimations. It is only under the mixed period efficiency estimations. So you want to also respectfully know that. The second fact that you got to understand is that some observations can have their projection point located on the horizontal or the vertical sections of the boundary when their super efficiency scores are estimated. Okay. In other words, when you estimate them, they will be, they will not touch the frontier. Okay. They will not be able to touch the frontier because they are moving in the same direction as the horizontal or the vertical section. Now, this is not usually clearer when we are doing input orientation under the radial measurement or output orientation under the radial. It is clearer when you are doing the input-output graph, input-output graph. And so when we come to the biennial Malmquist estimation, I will show you that, okay, for you to know infeasibility. But this normally can happen for some of the observations. You will not get their scores, and that will affect the results. So these are two important points you want to understand. Now, what I want you to do now is to be able to know how to formalize a Malmquist index for a journal paper or for a thesis writing. Because whilst we are going through the graph, it's critical that you learn how to formalize, theoretically formalize. Okay. So in order to formalize, we say things like this. Assume that there are n DMUs. That's the total number of DMUs. All of them are going to be assessed, okay, using M inputs and then S outputs. So M is the total number of inputs, S is the total number of outputs. We denote the Xij to the power T and theYrj to the power T, and then their T plus ones, okay, the inputs and the outputs of the DMUJ at time periods T and T plus 1, respectively, where I here. So watch it. I is the particular number of inputs. So their total number of inputs are M, and one of them is the I. Okay, and then the total number of outputs are S, and one of them is the R. That is why you have Yrj. That is the specific input of the Jth firm in time period T. The specific input of the J firm in time, because J2 is one of the DMUs. Okay, and their total number of DMUs are N. Now, the DEA-based Malmquist Productivity Change Index, okay, it will require that you formulate the following linear programming problem. Under the constant retention scale, this is how you model it. And this is important, okay? You guys have learned how to formulate envelopment model and multiplier models. You've learned that. If you haven't learned that, you check the previous videos, watch it, and then master that. Okay. So how do you now formulate the own period input-oriented efficiency score, which is theta T into bracket, the zero here is referring to the target DMUs that you are dealing with. That's a particular DMU at a point. So if you have 100 DMUs, you've got to formulate it for each one of them, tentatively speaking. So we do that. But we are doing it for time period T. So this is actually own period efficiency. How do you do that? This is how you write it. You write that theta star into bracket, the input-output combinations in that particular time period T, minimize. So this is the score you're going to get. This score will happen as a result of minimizing the theta, which but there are some slight differences, subject to all these mumbo jumbos. However, the most important thing is that you can see that each one of them have got what? A T. Okay? So there's a T, okay? For the frontier, sorry, for the technology set. Note that the left-hand side is a technology set, and the technology set has the frontier here. Okay, so here it means that the frontier technology is time period T, including the lambda. Now these ones, the frontier technology is important, And you can see that the individual input, all of them have got TTT, because we are dealing with own period efficiency. Now, if we were dealing with own period efficiency for year 2, it will be T plus 1, T plus 1, T plus 1 for all of them, okay? Now, so this is a theory, but how do you now do that for the particular firm? Let's do it for one firm. So you have the observations here. What I'm going to do is I'm going to do it for firm C or C1. Firm C in year 1, that one there. Firm C in year 1. We are going to formulate the input-oriented efficiency score for firm C in year 1, input-oriented. Now, what that means is that you are going to use these inputs, X1, you're going to use this input, X2, you're not going to touch the year 2, and you're also going to use this output, Y1. So as you know, is a weighted sum of the inputs less or equal to the input of the DMU under consideration. And the DMU now we are considering is the C1. So on the right-hand side, you're going to have 3, multiplying the theta, as you already know. Okay. Now, let's show that. Let's show that and see how it technically works. So we write theta 1 star, that is the C1 efficiency of a firm C in year 1 relative to frontier 1. This is achieved, this score on the left-hand side is only achievable by minimizing this theta for this DMU, subject to the output constraint. So I'm bringing the output constraint first. And you can see that the output constraint, you do 1, because they are all 1, 1, 1. You do 1 lambda 1, 1 lambda 1. You see, that lambda 1 is for firm A1 in that year. Okay. So when you are doing, you do 1 lambda 1, 1 lambda A1. Okay, we are doing it for this output. Okay, for this output. So 1 lambda A1, 1 lambda B1, 1 lambda B C1. Okay. And then greater than, because if its output is greater than the output of the DMU under evaluation, which is 1 theta. Okay, so that is how that one is supposed to be, 1 theta, or 1. But it's not going to be 1 theta because we are doing output orientation. So we are doing input orientation. And so because we are doing input orientation, the theta will have to be multiplied by the input and not the output. All right, so the second one is going to be 1, okay, you take this number x1, 1 lambda A1, 3 lambda B1, then 3 lambda C1, less than or equal to 3, which is the C1 here, is value, x1 value, 3, okay, less than or equal to 3 theta. And then you come and do for the second input constraint, 3 lambda A1, okay, 2 lambda B1, 3 lambda C1, okay, less than or equal to 3 theta again. And then you can now add your non-negativity constraint and or the VRS constraint if you are doing VRS, but in this case we are doing CRS. Okay. So that is how you do the formulation. You have to master how to do this formulation. It's very critical, very, very important to master how to do it. So once you've done this, then you can now add your non-negative constraint, which is this one there. In other words, the lambdas must be non-negative. Okay. If there was a VRS you were doing, you have to add a VRS constraint. The lambda 1, lambda 2, lambda 3, all of them added together should be equal to 1. So this is how you formulate the input-oriented one. Now, normally I would have asked you to do the formulation for some of the others on the screen. Okay. So I'm going to ask you, and then you will walk me through. Anybody who is able to do it, you walk me through. Okay. I'm going to ask you. So this was what we did for the own period efficiency score, which we calculated already and got 0.7778. Okay. Now this is a CRS, and not a VRS because we didn't bring the convexity constraint. Now, how do you do that for A1? Okay, so what we did was for C1. How do you do for A1? Okay, how would you have formulated the own period efficiency score for A1? I've started it for you. Okay, so somebody should walk me through it. You all have the data. Okay, so if you are bold enough, you raise your hand and you tell me how you would have done it. You are bold enough. Okay. Okay, so Michael is asking, why do we have greater than for the first constraint? Because it's the output constraint. The output constraint must have greater than or equal to. And the input constraints, and in this case, there were 2 inputs. So the input constraints must have less than or equal to. And again, this comes from the envelopment idea, because the weighted sum of the input should be less than the input of the DMU you are assessing. And the weighted sum of the output should be greater than or equal to the input of the DMU you are assessing. So this comes from the principle of the envelopment model. Okay. So that's our output. Is that? You're welcome. All right, so Morrison, I saw your hand. Are you ready to walk us through it so that we know? Yes, Morrison.
Right. Okay, so Doc, the function will be a minimum function, so to be theta star raised to the power 1 into bracket A1 is equal to minimum theta 1 into bracket A1. Then subject to the output part, which is 1 lambda A1 plus 1 lambda B1 plus 1 lambda C1 greater than or equal to 1. Then we look at the input side, and that will be 1 lambda A1 plus 3 lambda B1 plus 3 lambda C1 less than or equal to 1. Then for the second input, it will be...
Is it less than or equal to 1, or you have to multiply it by something?
It's less than or equal to 1.
What about
then multiplied by the theta, yes, because it's input oriented.
Of course, that's why I stopped.
Yes,
all right.
Yes, please. Then for the second input, it will be 3 lambda A1 plus 2 lambda B1 plus 3 lambda C1 less than or equal to 3 lambda. Thank you,
what?
Doc.
Less than or equal to
3 theta.
Exactly.
3
relax.
theta. All right.
Relax. You have eaten nicely. That's right.
Thank you, Doc.
So that's it. This is exactly what you said. But you've missed one more thing. Would you want to add it before?
The non-negativity constraint. So that would be A1 lambda. Sorry, that one would be lambda A1 plus lambda B1.
It's not plus.
Lambda A1 comma lambda B1 comma lambda C1 greater than or equal to 0.
All right. Okay.
Thank you.
So that's how you formulate it. That's what you have on your screen there. Okay. Guys, I beg you, learn how to formulate the model. Okay. These things might be quite long, might be quite boring, but that's how you understand things. That's how you understand things. When you jump steps, you tend to lose gaps. And when you lose gaps, there are gaps in your memory as well. Okay. So it's important to learn how to do this formulation. So this was the one that gave us the own period efficiency. It tells you how far the observation is from its own frontier period. All right. So the reference technology here can be switched. Okay. You can see that in both cases, we're using the own period. Okay. Now we can also, you're using year 1. We can also do for year 2, where this time everything is being measured own period as well. At this time, we are doing it for year 2. Okay, own period for year 2. Okay. So we can do the year 2 relative to FM in year 2 relative to frontier 2, own period. Own period. We can do that. Okay, and all of that. However, before the Malmquist can be calculated, it's important to get the two mixed period efficiency scores as well. Remember, in order to calculate the Malmquist, you need two own period efficiency scores. That is the one for the first period, the one for the second period. You need the two. So in this case, we are calculating for A, we need A1 own period and then A2 own period. Then we need A1 cross period and then A2 cross period. That's when we can calculate for A, okay? And so how do you do the cross period? This is a formulation of the cross period. And this is what sometimes you got to bring into your thesis writing and your paper. So watch it. You can see that this, you mention what is in the bracket, that is the efficiency, the observation. And then what is outside the bracket, but attached to the theta is the frontier. So this is a mixed period efficiency score for a particular firm. And it says that the efficiency of observation, the target observation, target for the representing the knot, the efficiency for the target observation in year T, but relative to frontier T plus 1 or T plus I. Please note that the T plus I can be T plus 1 or can be T plus 2. You can measure the efficiency score of anybody relative to any year. The only thing is that, you know, it's easier and to get for the adjacent year. So sometimes we say T plus 1, but it can be any number, T plus 2. So you can measure the efficiency of a firm in year 2000 relative to the frontier 2009. Yeah, it doesn't matter. They are not adjacent, but it's possible to do all of that. And you can see, I want to show you the theory before I let you formulate. Okay, this time I'm not going to go through the formulation with you. You will notice that in this case, if the observation was C1, it would have been C1 relative to theta 2. That's how it would have been. And then you can see that the technology set here, this left-hand side for all of them, the left-hand side is for the technology set in year 2, the same one as the one attached to the frontier. Okay, and then on the right-hand side is the firm observation, the target observation in year T, in the first year. And also, when you look at the lambdas, watch carefully, you are using the lambdas, okay, in year 2, in the second year, okay, in the second year. So you are not using the, so everything on the left-hand side is for the, in this case, the second year. Of course, if it has switched, it would have been the first year, but for the second year. So using your data, who can walk us through how we can calculate one of them? Okay, using this data, we want to calculate the cross period efficiency of C1 relative to frontier 2. Who can do that? C1, you got to be slow. Okay, if you rush, you'll miss it. C1 relative to frontier 2. Who can systematically walk us through that? Who is bold, strong, ready, and hungry, mentally hungry to want to really surprise us? Okay, so listen, the way you do it, somebody just sent me a message which is interesting. So it shows that I need to go through this one with you. Okay, so this is it. If we are doing for C1, okay, for C1. So first of all, let me use some write-up here so that at least you can follow me here. So we are going to have the C1 in the bracket, okay, and then the theta star will be to the power 2, okay, and then we are going to minimize, okay, the same thing, but without theta star. I don't want to write. Let me write. Okay. The same thing, but without theta star. Okay, subject to the output constraint first. And we know that the output constraint, and the output constraint here is for the year 2. So you are taking year 2 output. So it's going to be 1 lambda A1 sorry, A2, because we are doing year 2. 1 lambda A2 plus 1 lambda B2 plus 1 lambda C2 greater or equal to 1. Okay. That's for the output constraint. Then for the input constraint, there are 2 of them you're going to formulate. And you are going to use this one first, the X1. Okay, so that will be 1 lambda A2 for the first number plus 3 lambda B2 plus 2 lambda B3. Okay, less than or equal to that very input C1 that you are dealing with. Okay, remember you are dealing with that one. So it becomes 3 theta. Okay, so everything on the right hand side is going to be the observation, the target. And then everything on the left hand side is going to be the frontier. You're going to use it the second year. Now, the next one will be to formulate a constraint for year 2, year X2 in year 2. So that will give you 3 lambda A1 plus 1 lambda B1, sorry, 3 lambda A2, okay, plus 1 lambda B2 plus 3 lambda C2. Then you do less or equal to that very input under consideration. So it becomes 3. Then you attach theta to it. The theta here is indicating that we are dealing with input orientation. Then you do your lambda A2, comma, lambda B2, comma, lambda C2, comma, okay, greater or equal to 0. That's a non-negativity constraint. Okay, so you're able to do these formulation in that situation. Okay, nicely. Now somebody is asking me, you are formulating the efficiency of C in year 1 relative to frontier 2. And frontier 2, because it's frontier 2, everything you are using to form the frontier is going to be the year 2. That's it, frontier 2. Okay, so if you're able to do that nicely, that's what you get. Let me clear it and show you the results. Okay, so when you do that, you're going to get all of this. This is exactly what I did there. Okay, we're going to have all of this. Cross period efficiency, you got to learn how to master it. Okay, I don't know what Mike you are saying. The second constraint, you can see it here. The second constraint, that was it. Is 1 A2, 3 B2, 2 C2. They are all supposed to be 2 in year 2. Okay. If I wrote a typo, no problem. But the key point is that is the 2s that you are using. But when it comes to the right-hand side, because you are dealing with cross period, in this case, the one in the bracket is for the current year, in this case, C1. You will use that C1 data for the right-hand side. So if I switch it and I do C2 relative to frontier 1, you should be able to do that. Okay. If I do C2 relative to frontier 1, how would you have gone by it? Okay. If I do C2 relative to frontier 1, now what's going to be? C2 relative, you're going to use the information on the year 1 as a frontier. That's what you're going to use as the frontier. Then, because it's C2 relative to frontier 1, the information on the C2 will form the right-hand side. Okay. That will form the right-hand side for the theta. Okay. In an input orientation. In an input orientation. That's it. And I want you not to think only in terms of input orientation, because I could also give you a situation where you have to do output orientation. Now, when you have to do output orientation, the same thing. The only thing is that is the right-hand side that you will attach the phi, this time not theta, but you attach the phi to the output, not to the input, but to the output. Okay, so that is how you learn how to formulate this. You will do a lot of formulations. You will do a lot of formulations. So it's important you master this. Any question on this? Okay, so of course, this is the other one. This is the other cross-period efficiency. Okay, so you can see that in this second one, the frontier is the first year. They are all having T, the frontier. But when you look on the right-hand side, the target DMU will be using the second year and not the first year. Okay. Now, when you compare this with the previous one, you can see that the T and the T plus one, they were all swapped. That's all. The T and the T plus one, they were all swapped. And that's how you do it. And so you can do that for the second. In fact, the one I just did, okay, that's this for the C2 relative to frontier one. The one I just did, do that. That's it. And of course, when you do the calculation, you've already done the calculations already, and you can see that this was the value. So here's some important points to realize. Now, if you look at the own period efficiency, okay, the own period efficiency scores, you will notice that the own period efficiency scores are all less than 1 in an input orientation. And this same own period efficiency is 1 or less, okay, in an input oriented efficiency. Okay. Whether it is year 1 or year 2, it's 1 or less. It's 1 or less. Okay. But, and that is because you are inside a frontier. But the cross period efficiency, we have already said this, the cross period efficiencies can be less than 1, equal to 1, or greater than 1. Okay, they can. They can. That means, okay, they can. It doesn't mean they are always. And that will mean that if they are greater than 1, then they become what? Super efficient. Okay. But they can, when they are super efficient, then they can also be infeasible. Done that. Now, you guys remember that in the Malmquist, I told you that there are 2 kinds of the Malmquist. The first one was by Fair, Groskop, Lengren, and Roos. Okay, they published their paper in 1992. And that one dealt with the 2-factor decomposition. So you have the Malmquist, and then you also have the Malmquist split into 2. Then Fair, 1994, brought another Malmquist. This time, it was a 3-factor decomposition. They added a pure efficiency change. I'm going to just show you the first one, the 1992 one. Okay. First, we are going to estimate the Malmquist because we already have the efficiency scores already. And I'm going to do it for FEMC. This time, not C1, C2, but FEMC because we're putting the years together. And we are going to use all the 4 efficiency scores that we obtained for C. Remember, C, own period, cross period. C1, own period. C2, own period. C1, cross period. C2, cross period. That's what we're going to be using. Okay. But first, what is the formula for the Malmquist? You already remember, let me just give it to you. This is an input-oriented formula for the Malmquist. Please note, if it was an output-oriented, all that is going to change is just swapping, reciprocal. Okay. And if it was a distance function too, it will be the same thing. You swap. You swap. This is efficiency score, Farrell. If it was Shepard distance function, you just swap. You take the reciprocal of everything. So what is down goes up, what is up comes down. So this is an input orientation. Input oriented, not distance function, input oriented efficiency scores. And this is the Malmquist. Watch the top. You see that the top part is the own period for the first year. And here the down part is the own period for the second year. And then the cross periods are what you see here. All right. Now, we already have the score for the top one, all the 4. Okay, 1, 2, 3, 4, we have all their scores. Okay. Let's remind ourselves, own period efficiency score. Okay. What the Malmquist is doing is that you are taking the geometric mean, the square root, okay, the square root of the year. Now, if it was of the firms here, okay, of the year, so if it is 2 2 years, you can see. You just take the geometric mean, and then you calculate the Malmquist. And that's what you're going to do. And then we can now split them into that. Okay, so in the input orientation, there's something you want to know. We are going to know that the Malmquist, when you have the score, and this is a little bit tricky, but in order not to base on this, I will just tell you later on to swap the reciprocals so that these things don't confuse you. Now, in an input orientation, let me tell you the confusion first. When the Malmquist index is less than one, it rather shows growth. And that's why I'm saying that sometimes it can be a bit confusing. Okay. When it is less than 1, okay, that is growth in an input oriented. When it is equal to 1, then it shows that there is stagnation between the two periods. Okay. There's stagnation. And then when it is greater than 1, it rather shows decline. Now it's a little bit confusing because normally you expect that when it is greater than 1 is rather growth. And when it is less. So when you finish all your answers, just take the reciprocal of the answers. So let's say that you got the answer eventually to be 0.8. Just take the reciprocal, 1 over 0.8. And then whatever thing you get, now it will now reflect. So whatever thing you get, if it is greater than 1, then it is actually showing growth. And if it is less than 1, it is actually showing. But I wanted you to note that. Okay. And the R software we will use, it also goes by this. So the R software, I tend to take the reciprocal of all the scores. They can better explain. But when you use another software called MaxDEA, the MaxDEA will give you the results, all of them nicely organized, so that you know that greater than 1 is growth or improvement, and less than 1 is regress or deterioration. Okay, I thought I'll flag this before we move on. So let's go and do the calculation. Hand calculation first. Hand calculation. And that is why I told you keep all your scores. So now you're going to drop the scores into it. What we are going to do is I'm going to calculate the Malmquist productivity score for C, from C. And guys, go and check your results for C. You all have your results for C. Okay. I want to just move faster. When you check your results for C, the own period for C, which is a C1, that one was 0.778, the C1. And then the own period for C, which was the C2 score, own period, that one was 0.8, if you can remember. And then the cross period, okay, where you were calculating, and I'm doing the top one first, the cross period is, okay, the C1 relative to frontier 2. Okay, the C1 relative to frontier 2. That one, it was 0.875. You can check your results. And then finally, the C2 relative to frontier 1, that one was 0.667. So when you take your calculator, you now multiply the top part and then the down part and then divide each one. That will give you this value of 0.74. You take the square root and you get 0.86. What does this 0.86 mean? Well, first of all, it's less than 1. So it means that it is progress for input orientation. But in order not to be confused, you can take your calculator and then do the reciprocal of it. Somebody should take the reciprocal of this number and tell me. Just want to be sure that you are also on the same track with me. You take your calculator, you do the reciprocal of this. 1 divided by 0.8607. What did you get? I want somebody to do it. I want to be sure that you are doing something by hand. Because if I show you most of these results right now, you might think and convince yourself that you know. When in reality, you don't know. Okay. So when you do that, only one person has given me the answer. Okay. All right. 2, 3, 4, 5. Now everybody is giving me the answer. So you should get 1. The reciprocal will give you 1.16. 2 decimals is okay. Do you know why I wanted you to do that? Because now you know that it is progress. Now you know that FEMC has progressed from year 1 to year 2. And the actual progress is the number after the point. So the actual progress is 16%. So what it means is that this firm has increased its productivity, by 16% between the two periods. It's interesting to measure this because you remember that C was inefficient in both periods. C was inefficient in both periods. But you can see that using productivity, you can determine a certain trend. That's even though C is inefficient in both periods, is progressing. Is progressing. Is progressing. And that is the most important thing. The fact that, you know, you are somewhere doesn't mean that, you know, you are not doing well. You are progressing, and that is the most important thing. So it has improved its productivity by 16% or 16.2% in this case. All right. Now, if you go and calculate for firm A, you will see that it didn't get, you know, when you take the reciprocal like 1.162, it didn't get that. It got 1. It got 1. So firm A is experiencing stagnation, and stagnation is not the best. You want to progress. So firm A was efficient in year 1, if you can remember. And firm A was also efficient in year 2. So even though this firm was both efficient in both periods, it's not progressing. And that's not helpful at all. Okay. Firm B, if you go and calculate it, you will see that productivity had increased by 58%. So the firm has not just, this firm is good. It has increased productivity level. The firm has improved significantly over the 2 periods. Of course, before you can tell that a significant improvement, you have to bring the bootstrap into it, which we shall do. We shall do. Okay. And that will tell you that, oh, this progress was significant or it was not significant. But the one we did was C. And we know that C also experienced 16% improvement or progress between the 2 time periods. So this is just how to calculate the Malmquist productivity change index. And this is how we interpret the score, because it helps you to know how the firm is going. Now, we can now find the mean of all of these 3 firm scores. You can calculate the mean. You can add a 1, okay, to the point, blah, 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 blah. I mean, you can take all of them, and then you can now calculate the score. Okay, you remember that for the C, we had 1.162. We didn't take the reciprocal of the B, but when you take the reciprocal of the B, you will see that that one is giving you 1.581. That is why it is 58%, 1.581. Now, when you add that 1.581 to, when you take the mean, okay, when you take the mean of all of these scores, you will see that there is improvement in the industry. And you will now know who is driving the improvement. Okay. But again, guys, on each firm, for each firm, we need to know what is driving the performance. As for A, we know there's no performance drive here. Okay. B, we know there's a performance increase. And C, we know there's a performance. But what is driving? Is it the efficiency change or the technological change? And that is the next thing to deal with. Okay. That is the next thing. So in order to eliminate the assumption that, you know, the 2 scores should equal 1 and to allow technical inefficiency, what Farrell and Co did is to decompose the Malmquist into 2. One for efficiency change, the other for technological change. Now, the efficiency change, we said it the last time, is performance, your performance relative to yourself. So it's connected to managerial performance. And then the technological change deals with the industry dynamics, okay? The change as a result of research and development, as a result of process or product innovation. So when there's an innovation in the industry, you can capitalize on that technological progress and you can do well. Okay? You didn't bring the innovation, but then you can take advantage of it. And you see, sometimes a particular industry is doing well. So even though you are not doing well, you'll be forced to do well. For example, you go to Harvard. Maybe you are not that good, but you got some money, so you're able to go to Harvard. But because Harvard, there is that systems have been put in place for people to learn and be smart, you too take advantage of the dynamics in Harvard, and then you do well. And that is a beautiful thing about frontiership. That's a technological change. So how do you split that? Well, this is a split. Well, this is the one we calculated some few minutes ago. Now, to derive where the source of the progress is coming from, we split it into two. If I want to go and use change of subject and expand, you multiply the outside efficiency change here by the technical change, you will notice that you'll get back the same thing at the top. Okay? You can do that as your homework. Okay? Fish it out. Some of them will cancel, and then you'll get it. For example, this one, when you multiply the outside one by the inside one here, okay, taking into consideration the square root, you will notice that there will be some cancellations. Okay, there will be some cancellation. Okay, so this first one is efficiency change, and then the second one is the productivity change. Again, all these scores, you have them. You calculated all the efficiency scores. So all you have to do is to substitute. We're going to go to C again. Okay, and then we substitute it for C again. These scores, we know them. This value, we got it before. All of the values, you have them before. Okay. All of them, we have them before. So all you have to do is now use your calculator. Okay, take the square root here first before you multiply it by that. So you just go down, okay, and separate them, keep going down. This is your calculator's job. So you divide this by that, you get this, you divide this by that, you get that. And then you now take you multiply the two, you multiply these two. Okay. And that gives you this value of 0.837. Okay. Once you have the value, you just take the square root. You can see that we don't do anything to the efficiency change. You just take the square root, and then you get a score. Now watch these scores. If you want to, once again, find them in proper margins, you just have to take their reciprocal, because the scores you are getting here, even though we've used efficiency scores for them, but in order to best interpret them, you can take the reciprocal and then find them. So when you take the reciprocal of the first one, which is 1 divided by 0.9723, okay, you are going to get something like 2.8%. Okay, when you take the reciprocal, the value you're going to get is 1.028, which is approximately 2.8%. And then when you take the reciprocal of the second one, what do you get? Okay, you get 1.12, okay, let's say 130, which means that there is an increase of what, 13%. But here there's an increase of 2.8%. Now, so between and this is interesting, okay, for managerial policies, okay, for industrial policy, between the efficiency change and then the technical change, which one is driving the productivity more? What would you say? Which one? Is it the EC or the TC? EC or TC? So now you know that is TC. Excellent. So now when you are giving policies, the policies will be to increase that technology in the industry, because that is driving productivity a lot. Management are not doing that much. So it helps you to know the sources of the performance. So when you are driving a car, okay, you got to know the source of the performance of the car. What is making the car perform well? What is driving the performance? Okay, that is why we do the decompositions in order to find that. And this is exactly the example of that. So this formula, if this was an exam, you know what I would do normally? I will give you the formula here. I'll give you these two formulas, and then I will tell you to calculate that. Now, this is a two-part decomposition formula, but I can also give you a three-part. Okay, so look at this sentence. It says that progress is driven mainly by technical change. Technical change is the one driving the progress, but it's important to give the exact value, like we give 13%. So that is it. Okay. Now, everything that we have done here can be done in R. It can be done in R. Okay. But I'm not going to do the R now. What I'm going to do rather is to guide you on how to compute this using the three-part decomposition. So I'm going to use something here. So look at this very one. All that we did today is what you see. This is an output-oriented. Okay, this is an output-oriented efficiency score. But you can use the same principle to do that. Remember the score here. Okay, do you remember the score we had? Okay, we had a value of what? 0.9723. And then when we changed it, it became what? When we took the reciprocal of that, and this is important, that's what I'm showing. When we took the reciprocal, we got 1.028. Is that what you had? Come on, take the reciprocal and confirm. Okay, 1.028. That's what I think, but confirm. Okay. Let me see. Some of you are writing there. Excellent. Excellent. Okay, so that was it. 1.028. So keep this number in mind. That was a value we had, which we used to interpret. Keep this in mind. Okay. Now, when you go to this formula, which is the same thing as the one I gave you, okay, and I'm coming to interpret what I mean by the same thing as the one I gave you. So keep that number in mind, by the way, because I'm cleaning it. So when you look at this carefully, look at this. This is the one we just worked with. This is a fair Groskopf, Lindgren, and Roos formula. All right, the 1992 paper. Now, if you look at it, it is actually equal to, you see C22 at the top. So that C22 will be theta, okay, if we're doing, it will be theta T plus 1 into bracket X T plus 1, comma, Y T plus 1. That is how it would have been. Okay. That is how it would have been at the top. They are all T plus 1, T plus. Was it X and Y? Let me be sure. I just want to be sure what we use. Yeah. Just that we brought the knot under each one of them, but it doesn't matter. I've omitted the knot. Okay. Even though I've omitted the knot, it doesn't change anything. Let me just go back. Okay. So here, that's it. And then you do divided by, and I'm just writing what is at the top. Okay. Divided by the C11. Okay. The C11. Now the C here is representing like the constant returns, but don't worry. Okay. The C11. So how do you do that? Well, C11 here means theta T into bracket XT, comma, YT. Okay. Now, guys, I want you to find the values and divide and let's see. Find the values. You know the values for the top. Okay, somebody should write the values for me. Right there. So that will be what over what? Okay, so let me come down here. It will be something over something. What over what? Because we all know the own period for year 2 divided by the own period for year 1. What was the own period for year 2? For C. For observe DMUC. What was the own period? What was the own period? You have the scores already from you. We already have used these scores a lot. I just want somebody to type it up. Or somebody to. What was the own period for FEMC that we calculated for year 2? Come on, you can't get it. No, it wasn't 0.5, it was 0.8. You know, it was 0.8. What about the second year? Sorry, the first year. So 0.8 for the second year. What about the first year? Go and check your scores. Exactly, 0.778. Now divide the two and let's see. And you get the same answer that I gave you. So it gives you, the formula I'm giving you here, it gives you the answer straight away. When you divide the two, what do you get? You should get 1.028 or so. Exactly. You get 1.028. So you see, you don't have to do, what I'm saying is that you don't have to do the reciprocal that we did. If you use this formula at the top here, okay, as it is. Okay. But if I give you this formula, you might not fully understand. So I would have written it in this format. Now, the second part of the formula, okay, you might not notice yet, but this second part of the formula, okay, because it says times the second part. And look at the second part. The second part was 2,1. 2,1. Okay. Now I want you to look at that 2,1 very carefully. That is the one on the top. 2,1. Now let's go back to the formula that we used here. Okay. Look at that in there. I know this thing has covered you, but that 2,1, okay, that 2,1 is the one that is at the bottom here. It is the denominator in the square bracket here. Okay. If you look into that denominator carefully here, you will notice that it is a second year in the bracket relative to the first year frontier. Do you see that? It's a second year in the bracket. So the only thing is that everything down here has gone up and everything up here has come down. So when we go down, you will notice that that is exactly what is being done here. So this 2,1 here, okay, if you are writing it, it is the second year in the bracket. So it is the theta, the second year in the bracket. Okay, so it is theta, okay, with the second year in the bracket. So xt plus 1 in the bracket, comma yt plus 1, and then the first year as the frontier. Okay, so the second year in the bracket is rather 2. So the number 2 that comes first here, the number 2, the 2 is rather the one in the bracket, and the 1 is rather the one outside the bracket. Okay. And again, when you go and calculate this, it will give you that reciprocal answer directly. So how do you call this C21? Is efficiency of the firm in year 2 relative to frontier 1. So that one you go directly. Okay. Efficiency in year 2 relative to frontier 1. Okay. So C21. Efficiency in year 2 relative to frontier 1. What about C12? C12 is efficiency in year 1 relative to frontier 2. Okay. Efficiency in year 1 relative to frontier 2. So these are the formulae. Efficiency in year 2 relative to frontier 2. That's this. Efficiency in year 2 relative to frontier 2. All right. So keep that in mind. That is exactly what we worked. Now, this is the 2-factor decomposition. What about the 3-factor? The 3-factor is not called FLG, FGLR. No, it is called FGNZ, Fair, Groskopf, Norris, and Zahn. That was a 1994 paper. All they did is that they mixed this part, this efficiency change part alone. You watch the second part, they are the same in both cases. The only thing they did is that they calculated some of the scores relative to the VRS frontier and calculated some of the scores relative to the CRS frontier. So that's why you see that vein is there and C is there. Vein here means relative to the VRS frontier. And then they split them so that you have pure efficiency change, scale efficiency change. Guys, do you remember that when we were talking about normal technical efficiency, we said technical efficiency can be split into pure technical efficiency and then scale efficiency? Do you remember? All we are doing here is that we've added a change. That's all. The change has been added. That's it. Just the change has been added. So that is the same thing. So when you have this formula, all you have to do is to find the VRS score. And we shall do these things next time. Find the VRS score, find the CRS score, substitute them into these formulas, and then you can find so the fair Groskopf-Lindgren and Roos formula is 2 decomposition. Then the fair Groskopf, Norris, and Zahn is 3-factor decomposition. But guys, listen, because I want to end with this theory. This 3-factor decomposition was criticized by Ray and Desley. They criticized it. Do you know why they criticized it? Watch it. Because they said that this part here, you have CRS and VRS, CRS and VRS, CRS. But then when it comes to this part, there is no what? CRS and VRS. When it comes to this part, there is no CRS and VRS, CRS and VRS. So there is a problem here. And so they created a new one. And this is a Ray and Desley decomposition. Okay. So if you look at this part, CRS and VRS, CRS and VRS, CRS is the same, it's a similar thing, not the same. Okay. Okay. If you look at it, they have VRS, CRS, VRS, CRS, VRS, CRS, fine. But then the second part here, it didn't have that. So they created, and you can see that their second part here has VRS also inside it. And they called it scale change, scale change, scale change. So you have the pure efficiency change, then they call this pure technical change. Okay, so this pure technical change is pure, it's relative to the VRS. They are all V, pure technical change. And then the scale part alone is the one that must have the CRS, VRS, CRS, VRS, CRS. And so they created it. Okay. People believe that this one seems to be okay. Please know that they are just different ways of how people are looking at these things. But I prefer this Ray and Desley decomposition. Okay. So if one wants to calculate it, that is what the person will be using. Okay. I will not bore you with this in an exams, but I will bore you with this when you're writing your thesis as well with that. And then recently, not recently, okay, later on in 1999, Wheelock and Wilson also developed a 4-part, not 3-part, a 4-part decomposition. This is the one I like because it's not being used much. It also speaks volumes. So that one, the interesting thing is that the technical change, sorry, the efficiency change part, okay, the efficiency change part, there is both pure and impure part. There's a pure efficiency and there's a pure technological change. And then when it comes to the scale, there's a scale efficiency change and the scale technological change. So it's like the technological change, okay, you know, normal one, the 2-factor decomposition. The normal, we have the efficiency change and then we have the technical change. Okay, so what they are saying is that the efficiency change, there must be 2. And then the technical change must also be 2. What is that? The efficiency change must be pure efficiency change and then scale efficiency change. So this pure efficiency change is this one. The scale efficiency change is that one. And then they are saying that this technical change, the technical change must pick this one there, which is a pure technical change, and then the scale technical change, or the scale technological change. That is the 4-factor decomposition. I like that one because we've extended it recently. Okay. And what is interesting is that scale change part of Ray and Desley, the one we did before, the scale change, the latter part, that scale change part, it is made up of these two. Okay, these two here is the scale change part of Ray and Desley. Let me take you back slightly. You might probably get it. Okay. The scale change part of Ray and Desley. So this scale change part, this scale change part, it is made up of the scale change of Wheelock and Wilson here. So this is a 4-factor decomposition. And there are more, okay? But of course, we don't want to delve into. But these are the main decomposition of the Malmquist. We have the 2 parts, we have the 3 parts, and then we have the 4-part decomposition. Wow. This is knowledge, okay, learning. Okay. Okay. So what we are going to do next time is that we're going to take the data set and run all of this. It's when you give one command, all the scores will show. When you give one command, all the scores will show. We're going to run all of this, and then we will now make sense of every one of them. Okay. Ladies and gentlemen, that brings us to the end of the entire caboodle.